So we're here talking about concentration inequalities in Rocq. Welcome, everyone. Thanks. I sneaked this in. We start with a political statement, which is actually included in our paper, so you're welcome to read it. What we want to do is we want to certify elections. This is our original motivation for doing this work. And there's a very common statistical technique in elections that's targeted to give high confidence that the result of an election is not being tampered with, that the votes that are being cast are the ones that are being counted. And it's called risk limiting audits. And the idea is that if you have a paper trail, that means that either you vote on paper ballots like we used to, or if the election system is using some electronic voting machines with voter-verified paper audit trails, so that means the voter actually sees a physical copy of its cast vote, then we can have software independence. That means that using this procedure, we do not need to trust the software used to count the votes. But we can just do some statistical check, and essentially now this new statistical checks becomes our trusted computing base, right? So this is what we want to achieve. All these statistical procedures are essentially some variation of a concentration inequality. A concentration inequality is a statement of that form. This is our political statement, that if you have a random variable and you want to bound the value of the random variable to be above a certain threshold, and that should happen with a certain probability, let's say less than b, right? So if the random variable shouldn't deviate more than a certain amount from the threshold t. So this is the first part of our title, which is formalizing concentration inequalities. And for the second part, I want to talk about actually what makes our work nice in a way, the infrastructure and automation, which we introduce in MathComp and MathComp analysis. And specifically, we do that so that we can discharge range checks using lightweight abstract interpretation, reduce assumptions in probability proofs using LP spaces, and introduce semi-norms in the structure hierarchy while maintaining compatibility. So all a bunch of nice things that you can see in our library and make use of if you want. And then we formalize a bunch of concentration inequalities, including a library of general lemmas that you typically find in statistical textbooks like Markov, Chebyshev, Chernoff, and Cantelli's inequalities, and a bunch of others. And we showcase how this works well together with the Bernoulli sampling experiment. So about our motivating example, this is the Bernoulli sampling experiment that we do. And the statement is as such: given a bunch of independent Boolean random variables xi, all with probabilities of the variable equal to 1 being p, and two parameters, a confidence interval delta and the accuracy theta, so these two values that we try to wiggle around, then we have that if the number n of random variables is related in that particular way compared to theta and delta, then the probability of the composed random variable, which is the average sum of the xi's minus p, is less than theta. That probability should be at least 1 minus delta. So this is a concentration inequality. The random variable here is no longer, I mean, it's a composite random variable that we build by taking the average of a trial, right? And intuitively, this looks like what we plotted here. So this is just the normalized probability mass function for this sequence depending on n. So like the top line is 0 and 1, the two values if you only have one random variable, and then the curve sort of tries to converge towards a normal distribution as you increase n, right? So that's what we want to prove. And ideally, essentially, this gives us a bound of how many tests we want to make in order to get good precision in our estimate of the value p. So the plan for the rest of the talk is that we give you a bit of background on the measure theory and probability theory that we have in math comp analysis. We show you one technical issue that we solved, which is to accommodate semi-norms in the math comp hierarchy, which we extend. We show you how we handle automatically a bunch of useful side constraints that you need to prove about, like positivity or non-negativity of certain values, or some certain values being in the range of 0 to 1. For probability theory, that's very useful, and we do that automatically. We improve how we handle hypotheses in our probability theory library with the use of LP spaces, and then show you a bunch of concentration inequalities along with our running example, and finally we conclude. Yes? So on to the first point. This is a selection of the structures that we have for measure theory in math comp analysis, which is this formalization of mathematical analysis in Rocq as part of the math comp project. So we can start from the top where we have the structure of a content. All of these are so-called mixins in a tool called Hierarchy Builder. So they define some intermediate interface for each level of the structure. So content is just like a structure that has a measure that is non-negative, and for finite disjoint sets, you have that the measure of the union is the sum of the measures. An actual measure extends this for countable disjoint sets. And what we also care about are probability measures. So in a probability measure, we further require that the measure of the full set is 1. And these are all refinements over the structure, right? So at the end, once we have a bunch of these mixins, we can put them together with the so-called hierarchy builder factories, which you see here 2 examples. One is for measure and the other is for probability. Essentially, this factories put together all the mixins in the hierarchy of these interfaces. And so you get that the measure has, the measure 0 is 0. The measure of the empty set is 0. It's non-negative, and it's semi-sigma additive. And for a probability measure, you get all of that above, plus that the measure of the full set is 1. So once we have all this, it's easy to talk about random variables and expectations. And I have a little phantom there because this reminds me that essentially random variables are just measurable functions, right? So these are functions from a type T to R. The type T is the measurable type of the input space, and R is just the value of the random variable. But we record also with a phantom type that a random variable is to be interpreted under a probability space P. Once we have random variables defined as such, then we can define expectation as just the integral with measure P of the variable, right? And so essentially, this is the way we record the underlying probability space. So our first step was to actually introduce LP spaces. And to do that, we need the notion of a norm. A norm is essentially this function here, which for P finite is essentially the integral of the pth power of the absolute value of f to the power of 1 over p, right? And to the infinity, it coincides with the essential supremum if the measure is non-zero or 0 otherwise. And also, the actual definition we have is extended to negative values of p, which we need for other experiments. The interface that we had before in MathComp was this notion of a norm Z module, which has this bunch of requirements. We need to have a norm. We need to have the triangular inequality for the norm. We need to have some kind of scalar multiplication for the norm. So for natural n times x, the norm of that is equal to n times the norm of x. And that if you have a negation of the element, that's the same for the norm is the same as for the negated element. And the thing that this definition actually does not satisfy is this last bit, which we highlight in yellow, which is the fact that the norm is positive definite. So it does not satisfy that in the case that we have that the function f is non-zero only with measure 0, right? So we need to sort of split this into two other interfaces, and we want to do that in a backwards compatible hierarchy refinement. With the hierarchy builder, it's super easy, barely an inconvenience, right? You can split this interface into two mixins, one for the semi-norm Z module, which keeps all of the properties that are like highlighted in blue, but a positive definite property. And then we have a subtype for essentially saying that the semi-norm Z module is also positive definite. And with a factory, we can recover the previous interface that we had for norms, and we don't need to change any of the other code in our code base. So we essentially get that. Once we have norms and we have a nice interface for norms, we can build up LP spaces. LP spaces are essentially a set. The curly LP spaces are sets of measurable functions with finite norm. So we encode that with a new mixin, with a finite mixin for measurable functions with finite norm called isl function. And then we build this L-fun type, which is the type of measurable functions with finite p norm, right? And then LP spaces, we now build LP spaces on top of the previous notion by creating the equivalence class modulo almost everywhere equality. So you have that definition over here. Once you have that, you can, well, first of all, to prove that, actually, you need to show that NP is actually a semi-norm. So you need Minkowski's inequality that essentially is corresponding to the triangular inequality for norms. And to do that, you need a notion of convexity, which we include that it's very useful to have. So there's this definition that for all points in the interval type here between 0 and 1 of reals, then the function f applied on the convex operator of x and y with the parameter t is less or equal than the convex operator on the functions applied to fx and fy, right? So we have that, for example, for the power function, which is useful for us to prove Minkowski. But the clue here is to look at this interval 0 to 1, because that's the second thing we have for you, which is automating handling of interval types. The proofs that we built are full of side goals of non-negativity requirements or positivity requirements, or especially for probability proofs, we want to prove that some things are in the range 0 to 1. And here we highlight some of the things that we automate in our procedure. So we highlight a bunch of things that we can automatically discharge with our lightweight abstract interpretation that we build into the library. So how do we do it? We create this kind of interval types by combining a value r with a predicate that r is in a certain interval, right? And then we build for each operation a bunch of sort of automatic, well, first of all, I want to show you some projections from this interval type to numbers, and then back to intervals, which does the automatic inference. So all these things get automatically checked. For example, if you have a natural to which you sum 1, you get that this is automatically in the range 1 to plus infinity excluded. And if you take this thing, which is the division of 1 over 2 to the power of n plus 1, you automatically get a range that is strictly positive, and so on and so forth, right? So we looked at our library. We looked specifically for the sub-goals of the shape 0 less than something, or less than or equal to something. And out of 1,604 times that we find this in the analysis library, 729 are automatically handled by our procedure. So this is implemented by canonical structures, which is a kind of type classes. And essentially, we give one instance of this abstract interpretation method for each operator. And essentially, this is a lightweight procedure that gets us quickly a result, right? It's built by doing over approximations. So we tend to be coarse, but try to be useful. And whenever there's a refinement needed, we do that on demand. And it's available in MathComp. We pushed it back from MathComp analysis to MathComp, so you can try it also if you don't want to do analysis. Next, we look at how we improve handling of hypotheses in probability theory. So once we have all this nice infrastructure, one thing that's very useful often in probability theory is that we want to talk about whether something is integrable, whether we can actually discuss about the expectation of something. And as a consequence of Hölder's inequality, which we prove, you get that the LP spaces are included into one another. So LQ is included in LP if P is less or equal to Q. And as a consequence of this, one nice thing that you get is that if you need to talk about integrability of some random variable, no longer do you need to use the integrability interface, but you can use our interface for LP spaces. And so that amount of assumptions gets reduced to just 3. Essentially, when we put something in L1 P2, so the square of the function x, the random variable x, is integrable, that also allows us to automatically infer that also x itself is integrable by inclusion of LP spaces, and that also that x times z or y times z and so on are integrable because they are in L2, right? So all this gets automatically discharged. And we also highly reduce the number of assumptions that we make to the minimum set. Similarly, we use that also in our concentration inequalities. Here I show you Cantelli, for example, and you can see this is another equality of the kind that we bound the value of x in some way, and that gives us a bound in the confidence for that bound for the value itself of the function. So having that, we prove a bunch of other concentration inequalities, especially Markov, which we prove a general version of using a function f that can be used then to prove Chernoff and Chebyshev's. We only require that f is positive or non-negative for non-negative values of the parameter, and that is non-decreasing, right? And that you have essentially a general statement for Markov's inequality. We use that to prove Chernoff and Chebyshev and also Cantelli that we just showed before. All these are concentration inequalities of that kind that we showed at the start. And finally, we put it all together. We do so, well, by showing you again our sampling theorem, which is, again, one of these concentration inequalities. And we exploit nice properties of HB to create an interface for Bernoulli random variables. So Bernoulli random variables are just one satisfying the Bernoulli property. So the distribution of the random variable x is a Bernoulli distribution, right? And so we create a type called Bernoulli RV. And a Bernoulli trial is just a sequence of these random variables for which we create a composite random variable that's the sum for I less than n of every element of the random variable. We construct an operator called TNTH to take this sequence over the product sample space so that we can build the notion of independence. And then you have a bit of casting that we need from Boolean to reals and so on. Once we have that, we can talk also about a bound on the moment generating function. So the expectation of the moment generating function with parameter t is less than this exponential. And that allows us to build a bunch of nice concentration inequalities that are also in our experiment, which you find down here. And for that, we need the notion of the product of expectation when you have independent random variables constructed on the product sigma algebra, which we denote by this product here. So the expected value of the product of n random variables is the product of the expected values of each random variable, given that we construct independence that way. And we prove more Chernoff types inequalities, which are all concentration inequalities. Finally, our statement looks like this. So it says that if you take the value of the trial, so the sum of all the random variables in the sequence n tuple x, and divide by n, and theta and delta are, well, delta is between 0 excluded and 1 included, and theta is from 0 to p excluded. And if theta and delta satisfy that nice relation between them and n, then the probability of x, the value of the Bernoulli trial being further away to p than theta is at least 1 minus delta. So this proof applies the above inequalities and symbolic manipulation. We also solve some analytical goals, for example, bounds on x ln x, using math comp analysis and Coq interval. And I want to show you a bit now how we do that. So everybody knows that 1 plus 1 is equal to 2, right? And we know that if we are very pedantic, we can do things like prove it with some ITPs. And the first people who attempted to be very pedantic took 360 pages to prove 1 plus 1 equal to 2. So how long does it take us to prove e to the power of 2 less or equal to 8? Here's how long in the library. Essentially, we needed to prove this bound, that for x in the range 0 to 1 excluded, x plus x squared divided by 3 is less than or equal to 1 plus x times the logarithm of 1 plus x. This is a standard kind of analytical argument that you need to do. So the way we do this is we define that function f, and then we compute the derivative, study its sign, and use the fact that it's monotone in a certain range to reduce it all to just e to the power of 2 less than 8, which we need to prove, right? And you could do this by doing Taylor series manipulation, but essentially, nice thing that we have, well, it's not our contribution, but it's thanks to Coq interval, you can prove it automatically with Rocq, right? Without interval, we tried, and it took us about 100 lines on the first try, right? And since this is using the constructive reals that are defined in the Rocq standard library, and we are using our own definition of reals in math comp analysis, we need some conversions, which we provide. So we can go back and forth between the definition of exponential that you find in the Rocq standard library and our own definition. The proof is organized as such. We have a bunch of concentration inequalities, which we build starting from these analytical lemmas, some of the statements we showed you about the moment-generating functions of expectation, the Chernoff bound, and yes, this. And you can find all of our experiment, all of our material tracked in a PR, including a bunch of other contributions that have been merged back into math comp and math comp analysis. To conclude, let's give an overview with the related work. Essentially, we do interval analysis. That's one of our contribution. And this is nothing new in Rocq. Abstract interpretation of intervals has been done by Besson et al. In 2009, so nothing new there. And certified interval arithmetics, which we also use in our development, has been done also by Sylvie Boldo and Melchiong and we make use of it. Our contribution is more complementary to those because we integrate semi-decision procedures into the ITP, so into the library essentially, so that we can automate proofs, right? And they're meant to be lightweight and fast to use. And then a bit of comparison with other formalization of probability theories. In Rocq, we can see that there's InfoTheo, which has finitely supported probabilities. It's used in information theory, error correction, which essentially compared to the ISO formalization, we use the dependent types to encode LP spaces, which leads to nice automation, for example, for inclusion of LP spaces. And compared to MathLib, the use of canonical structures especially allows you to handle automatically the subtyping relation, so you don't need to introduce explicit casts. So that is some nice automation that we exploit in Rocq to make our library nice. Just for summary, we propose a formalization of probability leveraging Rocq and MathComp features. We use the Rocq type system to automate the ranging inference of values. We extended the MathComp hierarchy conservatively, so we don't break backwards compatibility with LP spaces. We leveraged LP spaces to enable succinct statements of basic probability lemmas and showed how this infrastructure can be put to good use to formalize a sampling theorem using several concentration of inequalities that we include in the library, and automation also, right? For future work, we want to port more results on, for example, conical spaces into the library, which we showed, for example, from using convexity. They're very nice to do our formalization of the theory. We generalize results towards formalization of complex statistical procedures. So we really want to have those political statements in our library. And we apply LP spaces to give semantics to logic used in machine learning. Those are also very nice things that we want to do. So thank you all for the attention. This is the bird from ITP, just standing out here, looking at you with Redberry. It's a red wing. Yeah, thank you.